In the last few classes, we were discussing about a free scalar field theory with action S is equal to minus half integral d for x del mu phi plus n square phi square. We have determined the field phi and its canonical conjugate momentum pi both in the k space, which is given by phi of k is equal to 1 by root of 2 omega k ak e raised to minus I omega k t plus a minus k dagger e raised to I omega k t. And the canonical momentum is equal to minus I root of omega k by 2 ak e raised to minus I omega k t minus a minus k dagger e raised to I omega t. So using this operator equation for the field and the canonical conjugate momentum, we can define all the commutators. Okay, we have found that phi of k prime commutator is equal to I del cube k plus k prime. We can also define the commutator between the annihilation and creation operator ak and ak dagger, ak prime dagger as 2 pi cube del cube of k minus k prime. And we have also concluded that after quantization, this theory will have an infinite number of decoupled harmonic oscillator that are labeled by these continuous parameters k. Okay, and we have already mentioned that the field theory is the continuum limit of particles on the chain. And now similarly, in the last class we have found the Hamiltonian or the total energy Hamiltonian operator for this case, and the Hamiltonian was integral d cube k by 2 pi cube ek by 2 ak dagger plus ak dagger ak. So in the last class we stopped here. So here we will continue from the Hamiltonian. Now I can rewrite this Hamiltonian H as integral d cube k by 2 pi cube ek, and then I can write commutator. So ak dagger I can rewrite. So here instead of ak dagger I can replace it with commutator of ak dagger plus 2 ak dagger ak, right? That's the 2 outside. So I can replace ak dagger with commutator of ak dagger, because when I have the commutator ak dagger, this will be ak dagger minus ak dagger ak. So I can replace ak dagger by the commutator of ak and ak dagger plus ak dagger ak. So this is equal to ak dagger. and already there is a AK dagger AK here, so this will be 2 times AK dagger AK. Okay, so that will be the Hamiltonian. Now if I see much more clearly, there is an integral d cube here and there are 2 terms here, so I can split the integral to the 2 terms. So H will be integral d cube k by 2 pi cube, then ek by 2. I have the commutator, yeah, so AK dagger. So AK dagger is given by 2 pi cube del cube of k minus k prime. So I can write, instead of AK dagger, 2 pi cube del cube of k minus k prime plus integral of d cube k by 2 pi cube. Then next we have ek by 2 multiplied by AK dagger AK. So we have 2 terms. If you see in the first integral, the 2 pi cube will get cancelled and I have ek by 2 integral d cube k del cube of k minus k prime plus, so here 2 and 2 will get cancelled, integral d cube k by 2 pi cube ek AK dagger AK. Now the first term will survive only if k is equal to k prime, which means when k is equal to k prime, this will be del cube of 0, right? So this will be integral d cube k ek by 2 del cube of 0. So this I can write as E naught. Okay, and that will be the 0 point energy. Now all the terms I can write as it is. ek AK dagger AK. Okay, so here this will be the 0 point energy. Integral d cube k by 2 pi cube ek AK dagger AK. So this will be the total Hamiltonian. So here there is something interesting. We can see that the operator phi of x comma t and pi cap of x comma t, they are both are time dependent. Okay, explicitly. And this time dependence disappear after the spatial integration. So we have already seen that e raised to I omega t will get cancelled when you do the spatial integration, that is when you transform from x space to the k space. But finally when you see the Hamiltonian is time independent, right? So the Hamiltonian is time independent. So this means that the time translation symmetry leads to conservation of energy. So I can say that time translation symmetry leads to energy conservation or conservation of energy. Okay, so there is no dependence on time since Hamiltonian is a conserved quantity. Now I can also make some remarks based on this. I can say that quantum field theory of the field phi reduces to a system of continuum of harmonic oscillator labeled by k with frequencies omega k equal to root of k square plus m square, because here you can see that this Hamiltonian is very much similar to the Hamiltonian of a harmonic oscillator. Therefore, I can make the comment that quantum field theory of the field phi reduces to a system of a continuum of harmonic oscillators labeled by k with frequencies omega k is equal to root of k square plus m square. So field theory can be written as the continuum limit of a chain of atoms or chain of harmonic oscillators that are connected by springs, and all of them are coupled oscillators. So you can decouple them and then find the normal spectrum. So how did you decouple them? So in the last few lectures I have explained that while finding AK and AK prime, I have to do the mode separation. So during that time we have actually done the decoupling. So you can decouple them and find the normal spectrum. Then each of them will be a harmonic oscillator. So by doing a Fourier transform, we are just diagonalizing those interaction between those springs. So here you can treat as if there are no interaction between the springs and they are all decoupled harmonic oscillator. So the field theory can be written as the continuum limit of a chain of atoms connected by springs and they are all coupled oscillators. You can decouple them and find the normal spectrum, then each of them will be a harmonic oscillator. Right. So what are the other conserved quantities that are there in this system? Other conserved quantities. So we have seen that Hamiltonian is conserved, or the total energy is conserved. Other conserved quantities. So in spatial translations, momentum is conserved. So which has the following Noether charge associated with the conserved quantity. So first one will be the momentum, which is equal to d cube x pi of x comma t phi of t comma x. So here this pi is the canonical conjugate momentum. This pi is the canonical conjugate momentum corresponding to the field, and pi is the physical space-time momentum. This is the physical space-time momentum. Okay, so you can simplify this expression. So you will get pi is equal to integral d cube k by 2 pi cube ak dagger ak. Then there is another symmetry that is conserved. Lorentz, so this system also has a Lorentz symmetry. We have already seen in the action that it is a Lorentz invariant. So Lorentz symmetry leads to a conserved charge which I represent as m mu nu. Okay, so first we have seen that time translation symmetry leads to conservation of energy. Then spatial translation, the momentum is conserved, and the conserved momentum is given by this expression. And the system also has a Lorentz symmetry, which leads to a conserved charge m mu nu. Now let's discuss about the 0-point energy. So once again I'll just rewrite the expression for 0-point energy. So 0-point energy E naught is given by 2 pi cube del cube of 0, because k prime minus k was 0. Then integral d cube k by 2 pi cube omega k by 2, or ek by 2. Here ek is equal to h cross omega. So h cross is 1 because we have chosen the natural units. Therefore I can write E as omega k. Fine. So this is the expression for 0-point energy. To analyze this part, we have to recall the definition of delta function. So what was the definition of delta function? Integral d cube x e raised to I k dot x is equal to 2 pi cube del cube of k. So this was the definition for delta function. Now here we set k equal to 0. If k is equal to 0, then you have 2 pi cube del cube of 0 is equal to integral d cube x, because e raised to 0 is 1. So integral d cube x. But we know that integral of d cube x is the volume of the full space, right? This is the volume of the full space. So this quantity 2 pi cube del cube of 0 is nothing but the volume of the full space. So now I can substitute it back to the equation for 0-point energy, right? So I can write E naught is equal to, instead of 2 pi cube del cube, I can write V. Then I have an integral, right? Integral d cube k by 2 pi cube omega k by 2. So integral d cube k by 2 pi cube omega k by 2. Okay. So here I represent this integral by epsilon naught, where epsilon has the implication of energy density. So the total energy E naught will be energy density multiplied by volume. Okay. So epsilon naught will be, or E naught will be the energy density, or the energy per unit volume. So energy density means energy per unit volume, which means if you take a unit volume, then the energy that is contained in this unit volume will be the energy per unit volume. So to get this, how do you get a unit volume? If you have infinite number of oscillators, then get by the lattice spacing tending to 0. So in quantum field theory, within any volume, then you definitely have infinite number of degrees of freedom, right? Because when A tending to 0, we have seen that it is a infinite number of harmonic oscillators, or infinite number of degrees of freedom. When you view it from a distant, then A tends to 0, right? So when you take energy per unit volume in quantum field theory, within any volume you will definitely have infinite number of degrees of freedom, and this will lead to the divergence of the energy density, which means that energy density is divergent. So one of the key differences between quantum field theory and quantum mechanics is the divergence arising from the number of degrees of freedom. The biggest part of quantum field theory is to understand how to treat these divergences. So what are the different ways to treat this infinity? So first you have to find a way to make it finite, and then you can either subtract it or divide or perform any other operation. And next you have to find the cutoff of the infinite series at some scale as a reference. You have to first set. Okay, so first you have to find a way to make it finite. First you have to make it finite, and the second step is to find a cutoff. So how do you get a divergence, which means the energy of the infinite number of harmonic oscillators, right? So plus 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 etc. You will have a lot of term in the series because you have to add the energies of all the infinite number of harmonic oscillators, and that is what is leading to the divergence. So you have to find some cutoff scale and you have to terminate the series at some scale of reference. So you have to find the cutoff scale and then approximate the value. So here we always keep a momentum cutoff. For example, k less than some scale, which is lambda. So here lambda will be a scale where quantum field theory is no longer valid. It is not mandatory that the quantum field theory must apply to all length scales, right? For example, in the lattice model that we are seeing, the scale might be 1 by a, right? 1 by the lattice spacing. So like that you have to find out some scale where you can cut off the series and then approximate the value. And even if you cut it off at a particular scale, still the energy density is pretty big number. Okay, so this 0 point energy cannot be ignored because it is measurable. In real life, you have quantum fields flying everywhere around. So, but we don't see a huge vacuum energy. This is another problem in cosmology, which is known as the cosmological constant problem. So this also relates to the divergence in the energy density in quantum field theory. Next remark what I have to make is about the Hilbert space. So we have seen that the Hamiltonian d cube k by 2 pi cube ek ak dagger ak plus the 0 point energy. The Hamiltonian is given by integral of d cube k by 2 pi cube ek ak dagger ak plus the 0 point energy. So from now onwards, we'll ignore this constant energy, which is known as the 0 point energy in quantum field theory, because it is just an overall constant and doesn't do anything in the Hamiltonian. So the lowest energy state is called the ground state or the vacuum state, right? The lowest energy state is known as the ground state or the vacuum state. Which is defined as ket 0. So this satisfies the annihilation operator acting on 0, you will get 0. For all other k, the general state will have the form nk1, nk2, etc. So this is for the vacuum state. For all other state, you will have something like this, which is proportional to the ak1 dagger, how many times? nk1 times, then ak2 dagger nk2 times, acting on the lowest state. Okay, or simply I can say a K dagger acting on the 0th state or the vacuum state will give you the kth state. So this is the simplest case that is possible. If I excite both K1 and K2, so how do I excite K1 and K2? So now I am exciting K1 and K2, so I will get K1, K2. So what is the physical interpretation? Okay, so if you have a Hamiltonian, if it acts on the lowest state, you will get 0. Then you have a momentum which is acting on 0, then you will get 0, right? So this is for the lowest state or the vacuum state. Now for a general state K, if Hamiltonian acts on the state, we'll get omega K, K, and momentum acting on K will get Ki, then the same state K. So here all these states I'll represent by vector K. Okay, so the state K has a space-time momentum, right, which I can represent as P mu is equal to omega K, K. So which is same as the relativistic momentum or the momentum of a relativistic particle of mass m. So this, okay, the state K has a relativistic momentum. P mu is equal to omega K, K, which is same as the relativistic momentum or the momentum of a relativistic particle of mass m. So relativistic particle of mass m. So that will be having omega K square is equal to K square plus m square, and P square is equal to minus m square. Now similarly, if I generalize for the state K1, K2, so this is another state K1, K2. So first we have seen for the lowest state or the vacuum state, then we have seen for the simplest state which is K. Next we will see K1, K2. So the energy eigenvalue for such a state will be given by omega K1 plus omega K2. Okay, and the momentum will be K1 plus K2. Okay, so here E and K are the eigenvalues of the Hamiltonian and the momentum. So we can interpret it as two particles with momentum omega K1, K1 and omega K2, K2. So you can do this to any state. For example, if you have more than one state, nk1, nk2 plus etc., corresponding to nk1 particles of momentum K1, nk2 particles with momentum K2, etc., then this can describe any number of particles, right? So first we have seen vacuum, which means there are no particles. Then we have seen state K, where you have a particle of mass m with momentum omega K, K, and then you have here, you can see there are two particles with energy and momentum omega K1, K1, omega K, K2. So you can do this for any state. For example, if you have nk1, nk2, etc., so this is a state, then this will correspond to nk1 particles with momentum K1 and nk2 particles with momentum K2, etc., right? So this can describe any number of particles. So mathematically it can be viewed as the harmonic oscillators, and each excitation of the harmonic oscillator corresponds to a particle from space-time point of view. Okay, so that is very important here. So we have seen that the system itself is a harmonic oscillator, and when you do the excitation, which means ground state, there are no particles. When you go to first state or the next simplest state, then you have one particle, and the more state, as you increase the state, then you can see there are more particles. So mathematically it can be viewed as the harmonic oscillators with each excitation, right? Each excitation of the harmonic oscillator corresponds to a particle from the space-time point of view. Okay, and we can also see that the commutator AK1, AK2 dagger, AK1 dagger and AK2 dagger is equal to 0. So this commutator shows that there is a symmetry in permuting all these different particles in any general state. So which tells us that these particles are bosons, right? So these commutators show that there is a symmetry in permuting all the different particles in any general state, which means AK1 dagger, AK2 dagger minus AK2 dagger, AK1 dagger is equal to 0, which means AK1 dagger, AK2 dagger is equal to AK2 dagger, AK1 dagger. Okay, so there is a symmetry in permuting all these different particles in any general state. So this tells us that these particles are bosons. So now we have seen that each excitation of the harmonic oscillator corresponds to a particle, and also the symmetry in permuting these different particles shows that these particles are bosons. So this becomes a bosonic field theory. And the next interesting fact is that all the particles have positive energies. Okay, even though you have E square is equal to P square plus M square, when you look at a physical state and the eigenvalue of the energy state, all particles will have physical energies. So there is no negative energy problem here, right? Because the eigenvalue of the energy state is positive. So there is no negative energy problem appearing here. All the particles will have physical energies, and total energy of a state will be equal to the sum of energies of all the particles. Okay, so this also says that there is no interaction. So here in the Hamiltonian you can see that, okay, so this is a very good evidence that there is no particle interaction. This is a free particle theory, which means the particles do not interact with each other. That is the meaning of free particle theory. So here you can see that the total energy of a state is the sum of energies of all the particles, which means that there is no extra energy or there is no interaction, and that's why this is called the theory of free particle. Theory of free particles. There is no interaction between the particles. Good. So next we'll see how to normalize the state, right? So you have already learned the normalization condition psi star psi for a wave, right? If you have a wave function psi, then how do you normalize the wave function? Psi star psi is equal to 1, and then you will find the normalization factor, etc. Similarly here, let's look at the state. So here you have a state, so you have to see the normalization. So we have a state, and if AK dagger acts on the vacuum, then you will get the state K, right? So if I do the overlap K with K prime, if I do this overlap, then I'll get, if this is K, then what will be this K? This will be AK acting on the vacuum state. So I can substitute here, then AK prime dagger acting on 0. So here I can write AK dagger prime as the commutator AK prime dagger plus AK prime dagger AK. So this will be the expectation value of AK prime dagger commutator plus, so here AK acting on 0 will be 0. So whatever the other operation is does not matter because it is 0. So what is the expectation value of AK dagger? That will be, we already know it is 2 pi cube del cube of K minus K prime. So here this Dirac delta function is not a good object. So in quantum field theory, if you say something is not a good object, it means that it is not Lorentz invariant. So this is not Lorentz invariant. Therefore, instead of this state K, we have to define another state. So the new state I'll just represent by K. So the old state is vector K, and the new state is K is equal to root of 2 omega K vector K. Okay, which means this will be root of 2 omega K. What is vector K? AK dagger acting on the vacuum state. Now in this case, the overlap of the new state, that is K prime, will be equal to 2 omega K, because root 2 omega will be 2 omega, then 0 AK prime dagger 0, which means that this will be 2 omega K 2 pi cube del cube K minus K prime. Okay, so this is a good function. Okay, so this will be a good object in terms of quantum field theory, because omega K multiplied by the Dirac delta will transform smoothly under the Lorentz transformation. Okay, if you act a Lorentz transformation on state K, then for example U lambda acting on the state K, then you'll get lambda K. So here U lambda is the quantum operator to generate the Lorentz transformation. Okay, so U lambda is the quantum operator to generate the Lorentz transformation. And lambda K is the Lorentz transformation acting on K. So general single particle state will have a following form. Psi is equal to d cube k by 2 pi cube f of k acting on k. So here f of k is the arbitrary function of k. It's an arbitrary function of the vector k or the state k. And you integrate over the spatial momentum here, right? So by choosing appropriate function f of k, you can construct a local wave packet. So you can choose f of k to construct a localized, means localized in space, right? A wave packet that is localized in space. Similarly, in the state k1, k2, okay, here each is a plane wave. They are not localized. They corresponds to two particles. So using integral d cube k1 by 2 pi cube d cube k2 by 2 pi cube f of k1 k2 acting on the state k1 k2. So using this integral you can construct two widely separated wave packets, and these are genuine two particle state, and the new state may be represented as the plane wave version of the two particle state. This is the new state, right? And the new state may be interpreted as the plane wave version of the two particle state. In that case, what will be the structure of the Hilbert space? So since there is no interaction between the particle, we can just separate it into the vacuum state, one particle Hilbert space, two particle Hilbert space, etc. Therefore, the full Hilbert space will be, I am representing it by script h, the vacuum state plus one particle Hilbert space plus the two particle Hilbert space plus etc. Okay, and the set of the states with a finite number of particles is called a Fock space. The set of states with a finite number of particles is called a Fock space. In the Fock space, we only have states with finite number of particles. So strictly speaking, all the states, that is vector k, then the ordinary k, then k1, k2, so these are all not normalizable. So they are not in the physical Hilbert space. So they are only plane wave normalizable, right? These are all, actually they are not normalizable in Hilbert space, in physical Hilbert space. In physical Hilbert space, okay, they are only plane wave normalizable. Okay, if you have not understood this concept, then just think about the wave function psi is equal to e raised to ikx. So in the normal non-relativistic quantum mechanics, we say that this is not possible, right? This is not a genuine physical state. So similarly, here also we have the state k, vector k, k, k1, k2, etc. that are not normalizable in physical Hilbert space, but they are only plane wave normalizable, right? Therefore, we can say that the state psi, which is equal to d cube k by 2 pi cube f of k is normalizable only for a proper choice of f of k. Okay, then the normalization of this state psi will be given by psi is equal to d cube k by 2 pi cube mod f of k square, okay, which is less than infinity, or I can say this is finite. So we can choose a basis of fi. So what are we have said that you need a proper choice of f of k in order for psi to be normalizable. So all the values of f of k may not be a proper choice. So if I take all the function fi and make it a set, so these are the possible fi's, okay, so that the psi is normalizable, and such a basis of phi is called the set phi I. Okay, so we choose a basis of fi and then define alpha I is equal to d cube k by 2 pi cube fi of k acting on k. Okay, so how do you make it finite? So I am taking a proper choice of f of k such that it is normalizable, and if I apply those f of I here, then I am defining all the normalizable state. So here alpha I is the basis of the single particle normalizable state. So alpha I gives the basis of the single particle normalizable state. So K forms uncountable continuum. But once we impose the normalization condition by choosing the normalizable fi, the basis of fi, then the normalizable states are countable, right? Then the set of fi, these functions are countable. Which means, so what is the meaning? The one particle Hilbert space is actually generated by countable basis. Okay, so that is K. So K was actually uncountable continuum. Then when you may choose fi such that the set fi are all the basis of all the possible fi are countable, then the one particle Hilbert space is actually generated by countable basis. Fine. So next we see the role of Noether charges. In classical mechanics, if an action is invariant under a continuous symmetry of the infinitesimal form. For example, phi a prime is equal to phi a plus epsilon alpha fa alpha of phi a. Okay, so in classically, if an action is invariant under a continuous symmetry which has an infinitesimal form, then the conserved current J mu alpha is such that del mu J mu is equal to 0. So here alpha labels different transformation or symmetries. Okay, different transformations. For example, alpha equal to 1 means it may be translational transformation. Alpha equal to 1 means maybe 2 means it can be Lorentz transformation. So there are different transformation, and alpha will label all those different transformations or symmetries, and A labels the fields, different fields. Okay, so we have already seen that the general form of the Noether current will be of the form J mu alpha is equal to partial derivative of L with respect to del mu phi, then Fa alpha minus K mu alpha. Okay, and the transformation is such that the variation in the Lagrangian density will be epsilon alpha del mu K mu alpha. Okay, and correspondingly you have a conserved charge Q alpha. Okay, so corresponding to each symmetry you have a conserved charge Q, which is equal to integral of d cube x J alpha 0. So this is classical. In quantum level, the commutators between the charge and the field generates such a transformation, okay, that is infinitesimal transformation, in such a way that, so in quantum, so what we have seen is in classical. In quantum level, epsilon alpha Q alpha and the field phi a commutator will give minus I epsilon alpha Fa alpha. So this is the infinitesimal transformation. So by exponentiating the charge, that is e raised to I lambda q. So by exponentiating the charge, you get a operator. So let this operator be u lambda cap. So this is an operator. So when this operator acting on phi generates finite transformation, okay, so u lambda acting on phi a, okay, will generate phi a prime. So when this operator acts on phi, it generates a finite transformation. Okay, so this we will see in the next class. So for the time being, we'll stop here because we have some time constraints. In the next class, we will see how to get the finite transformation.